Okay, so good day everyone. This is Sunil Kumar Pradhan. In this session, we'll going to discuss about some questions and solutions on electronic materials and devices. And let's see, first question here. The energy formation of a vacancy in the aluminum crystal is about 0.70 electron volt. Then calculate the fractional concentration of vacancy in aluminum at room temperature, that is at 300 Kelvin, and very close to its melting point 600 degrees centigrade. That means you have to find out what is the fractional concentration of aluminum at room temperature. That means at 27 degrees centigrade, that means at 300 degree Kelvin. And another, at the melting point of aluminum is 660 degrees centigrade, then what is the fractional concentration at its melting point? The second question is, what is the vacancy concentration at 660 degrees centigrade, given that atomic concentration of aluminum is given 6 into 10 to the power 22 per centimeter cube. Okay, so what is the vacancy concentration at 660 centigrade? So how can we solve this question? Now, if the number of atoms per unit volume in the crystal is n, if n is the n, that means capital N, which is mentioned here, is the number of atoms per unit volume in the crystal, then the vacancy concentration is, let's say, Nv is the vacancy concentration, and n is the number of atoms per unit volume, and Ev is this energy. Then K is the Boltzmann constant and T is the absolute zero temperature. Then uh, then your Nb is equal to N into e to the power minus Ev by Kt. Okay. Now this what is this? The energy formation of vacancy, that is your Ev, is already given 0.70 electron volt. Now this Ev we can put it here. So e to the power minus 0.70 Ev, and into 1.6 into 10 to the minus 19, because you have to convert it into joule. So and K is the Boltzmann constant is nothing but 1.38 into 10 to the minus 23 joule per degree Kelvin, and T is the absolute zero temperature. So this fractional concentration at 300 degree Kelvin will be 1.7 into 10 to the minus 12. We have to adapt the same thing at 660 degrees centigrade. But before that, we have to convert 660 degrees centigrade into degree Kelvin. So that is your 933 Kelvin. So 660 plus 273 will be 933 Kelvin. So what is my fractional concentration here? E to the power minus Eb by Kt. Eb is given 0.70 Eb. That if you convert into joule, so it is 1.6 into 10 to the minus 19 joule, and K the Boltzmann constant 1.38 into 10 to the minus 23 joule per degree Kelvin. T is the temperature, that is 933. So your fractional concentration will be 1.7 into 10 to the power minus 4. Now, what is the atomic concentration? Now, if atomic concentration N in aluminum is 6 into 10 to the 22 per centimeter cube, is already given in this question, then what is the vacancy concentration at 660 degrees centigrade? So vacancy concentration 660 degrees centigrade will be 6 into 10 to the 22 per centimeter cube into 1.7 into 10 to the minus 4, which is which we find out previously. So your vacancy concentration will be 10 to the power 19 per centimeter cube. Okay, so this is the solution to this question. The next is, given that the density of states related to effective masses of electrons and holes in silicon are approximately 1.08 ME and 0.60 ME. So what is ME? ME is the mass of electron, that is nothing but your 9.1 into 10 to the minus 31 kg. And electron and hole drift mobility at room temperature are given 1400 centimeters square per volt second and 440 centimeters square per volt second. Now question is here, what is the intrinsic concentration of silicon? And second, calculate the intrinsic resistivity of silicon. So this is the question here. So how can we solve? Now, if the effective density of states, that is density of states at the conduction band H and density of state of valence band of H, is given by this relation. So 2 into 2 pi me star kt divided by h square into 3 into to the power 3 by 2. Similarly, density of state at valence band H is given by 2 2 pi mh star kt by h square 3 by 2. Okay, this me star and ms star is nothing but effective mass of electron and effective mass of hole respectively. Okay. So if you can put all this value which is given in the all the values are given. So if you can put the values here, so we can find this density of static conduction band is 2.81 into 10 to the 22 per meter cube, and density of static valency band is 1.16 into 10 to the 25 uh, uh, 25 per meter cube, okay, or 1.16 into 10 to the 19 per centimeter cube. Now, this intrinsic concentration is related with this density of states at conduction band end, and valency band is related as NCMB square root and e to the power minus Eg by 2 kt. Okay, so this is the relation. T is the Boltzmann constant, T is the absolute zero temperature, and this what you can say, this value is already given. So if you can put the value here, band gap, as you know, for this is 1.1 electron volt because it is silicon. As you know, it is 1.1 electron volt. So and if you put the values, intrinsic concentration will be 1 into 10 to the 10 per centimeter cube. So how to find out the conductivity here? As it is the intrinsic silicon, so conductive your mobility of electron and mobility of hole both will be taken into consideration. And as you know, for intrinsic carrier concentration, your intrinsic carrier concentration is equal to your electron concentration and equal to your hole concentration. So that is nothing but your intrinsic carrier concentration. So it is 1.6 into 10 to the 19 coulomb, the charge of electron. Now intrinsic carrier concentration already given 1 into 10 to the 10 per centimeter cube, and mobility of electron 1400 plus mobility of 440. So if you can put all the value, it will 3 into 10 to the minus 6 ohm inverse centimeter inverse. So what will be my resistivity? Resistivity is nothing but 1 divided by conductivity. So it is 3.3 into 10 to the 5 ohm centimeters. So this is the solution here. The next question is the electron concentration in a sample of non-uniformly doped n-type silicon at room temperature, that is at 300 Kelvin, varies linearly from 10 to the power 17 per centimeter cube at x is equal to 0 to 6 into 10 to the 16 per centimeter cube at x is equal to 2 micrometer. So now, this is nothing but the question is given, your concentration gradient is given. Okay, with respect to distance, what is the concentration variation? Now, assume a situation that the electrons are supplied to keep this concentration gradient constant with time, and electronic charge, as you know, 1.6 into 10 to the power minus 19 coulomb, and diffusion constant is 35 centimeters square per second. Then find the current density in the silicon if no electric field is present. Okay, so electric field is 0 here because no electric field is present. So what is the current density? So current density, as you know, current density will be summation of your drip current density and diffusion current density. But drip current density will be 0 because there is no electric field. So what will be the current density? That is only due to your diffusion current density, right? So if you can, so this is the relation. So the total current density to electron will be your drip current density and plus diffusion current density. But electric field is 0, so diffusion current density will be also, sorry, drip current density is also 0. So only remaining is your diffusion current density. So that is equal to dne into dn by dx. Okay, so your dn by dx is coming to be minus 2 into 10 to the power 20. Put the values here. Okay, and this is dn by dx, and then your diffusion constant is already given 35, and dn by dx we find out here. Electron charge is 1.6 into 10 to the minus 19 coulomb. So what will be my current density? This current density is due to diffusion current density, so it is coming to be minus 1120 ampere per centimeter square. Okay, so this is the solution of this question. Next question is, a sample of germanium is doped to the extent of 10 to the power 14 per centimeter cube donor atoms and 7 into 10 to the 13 per centimeter cube acceptor atoms. At the room temperature, the resistivity of pure intrinsic germanium is 60 ohm centimeter. If that applied electric field is 2 volt per centimeter, then find the total current density. This is the question here. How to solve? You see, for the pure germanium, as we know that intrinsic current concentration will be equal to your electron concentration and hole concentration. So what is my intrinsic current concentration? That is your conductivity divided by summation of your mobility of electron and hole multiplied by charge, electron charge. So if you can put all the value here, so it will be coming as 1.86 into 10 to the 13 electrons per centimeter cube. Now for intrinsic semiconductor, as you know, your multiplication of your hole and electron concentration will be equal to your Ni square. And as for charge in electrical neutrality, your E plus Nd is equal to Na plus N. E is your hole concentration, Nd is your donor concentration, Na is your acceptor concentration, and N is your electron concentration. So what is P minus N here? It will be Na minus Nd. Na and Nd is already given in the questions. So it will be minus 3 into 10 to the 13. And if you can solve this question, then it will be coming as electron concentration will be 3 into 10, 3.88 into 10 to 13 per centimeter cube, and hole concentration will be 0.88 into 10 to 13 per centimeter cube. Okay. So this is the thing because this electron hole concentration we can get solving these two equations. This is the first equation, P into N into Ni square, and P minus N is equal to minus 3 into 10 to 13. Now what will be my current density here? That is equal to N mu N plus P mu P charge into electric field. So finally the current density will be 52.24 milliampere per centimeter square. Right. So I hope you understood the problems and solutions. Uh, so if you like the effort, you please like and subscribe. And if you have any queries, please feel free to ask in the chat box here, and I'm happy to answer all the questions. Okay, so so let me know if there is any queries uh, as per the questions which we have solved here. So with this, let's conclude this session. Thank you, everyone.